Okay. Okay, so for variation of parameters, what we did is so here's the general equation here. So what we did is basically we say well h is c1y1 plus c2y2, and we let yp equal to this. Okay. And then we substitute this yp prime and yp double prime back into this differential equation. We try to solve a possible value of m1 and m2 such that yp is this particular solution, right? So we got m1 equal to something, m2 equal to something, all right? Yeah. So the only thing I want to point out here is the solution that I give it to you at here, okay? It's based on this one here. So you look at this one here, what's this? Basically I'm saying the coefficients here is 1. Right? Here's A, here's B. So the formula that we derived in the first lecture, okay, that's for this particular case here. Let me rewrite the formula here, okay? However, you need to be careful. Basically, if the question giving you here, if this is not one at here, if there's something else at here, right? So the first step you need to do is you want to use that formula, you have to normalize it, okay? Yeah, so. Okay, so what happens is basically if what you have here is this, for example. Maybe use a different number here. Let's use a capital A here. Okay, if what you have here is this, you can divide both sides by A first. That's no problem at all, and then use this formula. Okay. Otherwise, you can actually derive another set of the formula based on this second-order differential equation by going through the same procedure here. Okay. So if you do that, actually what you can end up with is this. So m1 of t equal to bottom here is WTA, like this. Okay, so notice the slight difference here, okay? So when the coefficient here is 1, there's nothing here, right? But when it's A here, the M1, M2, there's A here. Yeah. Just wanted to point out this difference here, in case. Okay, so what we're going to do is basically we're going to look at application of second-order homogeneous ODE. So far, it's a purely mathematical approach, you know, giving a second-order non-homogeneous, and how do we obtain the solution, right? Yeah. Now let's take a look at the practical meanings, or in actual situations, right? So what we're going to learn, what we're going to look at is so-called forced vibration. Okay, so forced vibrations. So second order ODE, and we know that it can come from a different kind of system. It could be mechanical, it could be electrical, or it could be some others. But we have been using mechanical system, mass print damper system for illustration. Okay, so this is the simplest mass print damper system. All right. So let's use this system for illustration of this forced vibration again. Okay. Yeah. So again, I'm not going to using any numbers. Everything is purely symbols here, right? Yeah. So first, number one case, okay, when we were talking about homogeneous one, number one case is free vibration, number one case is no damping, right, undamped. So same thing. So let's say we're going to look at undamped system. Yeah. So this time we will have a certain kind of a force at here now. Okay. So for undamped system, that basically means the B term equal to 0. Right? B term is 0. Then our equation for motion will be m. Let's see if I use a y. As that lecture use y, I'll stick with y here. My double prime plus ky, okay, equal to this input. Okay, to the input. Okay, so now we're talking about vibration in here, right? So this is sort of a specific application. When you want a vibration, basically that has something to do with is this input at here. So what kind of input will induce this vibration, right? Yeah. So we're gonna give our input a specific kind of input, which is sinusoidal input. Okay. Yeah. So we're gonna change this one here. Let's say, suppose that my input is a sinusoidal input. Okay. So let's say it has an amplitude f0. And it has a frequency omega. Okay. So I'm not specifying the frequency here. The reason is basically you can vary your input frequency. Okay. So that's actually one kind of a very powerful analysis approach. So basically what happens is there is a so-called approach called frequency response. And frequency response basically means you inject a spectrum of different frequencies of input into the system. Okay, so for example, you inject 1 hertz, 5 hertz, 10 hertz, 100, 1000 hertz, right? So different input with different frequency. Okay, then you observe the system response. So you record the data. Okay, you record the data, record and the amplitude of the response, record the phase of the input, the response. Okay, then you will have the so-called frequency response. Okay, so we'll talk about that in more detail when we're in the Laplace transform, right? So keeping this format here, basically it's a format of giving a different frequency of input into the system and observe the output here, right? So the output, okay, will have vibrations basically. And so how does the system vibrate? And that's what we call the so-called forced vibration. So you inject a certain sinusoidal input. You want to induce vibration. So that's what we call forced vibration in here. All right? Yeah. So let's take a look at this one here. Okay, let's take a look at this first case undamped system. So basically what we have here is a non-homogeneous, okay, with a sinusoidal input on this side here. So now you think about the general approach of solving this kind of system, and you have two different methods now, right? You know, method of undetermined coefficients and the variation parameters. So if either way, you know, your first step you do is you're gonna have to solve this homogeneous first. So your YH, I think we have been doing this quite a bit. So your YH here, for this particular solution here, your YH is going to be A cosine omega nt plus B sine omega nt. And omega n is K over M. Right. Was that clear? Yeah.
Why did you choose the sinusoidal only?
Because I wanted to induce vibration. And I wanted to look at the so-called frequency response. That's why you inject the sinusoidal input. Okay, yeah. So we're dealing with a linear system. One of the features of the linear system is you inject as a sinusoidal input, it will spit out the sinusoidal input, but with a different amplitude and a phase. So that's the nature. Actually, we're gonna look at this later. Okay. So then, what happens here is the information of this different amplitude, different phase, right, will give you a sense of this characteristic of the system. As a matter of fact, you see, what do we mean by a characteristic system? See, some systems respond fast, right? And some systems respond slow. So how do we characterize this concept of fast or slow? Actually, that's the phase angle. The phase angle is how fast or how slow you're responding there. Okay, you have a large phase angle, you have a large delay, and you give an input there. Okay, it's not responding to you as immediate as possible. Okay, so that's basically the reason you inject the sinusoid into system there. You want to look at how the system responds, right? How the system responded to your input there. Okay? Yeah. So there is a very significant meaning in here actually. So your homogeneous solution is this one here. Okay, then here's my input here. So now if I want to use my undetermined coefficient methods, then I need to come up with a particular solution, YP, right? Yeah, YP is a lucky guess method. So when you come up with a different solution for the YP, so what do you have to do? You come up with a solution based on the table, basic solution here. So that's probably, let's say this is AB, right? Let's use a C cosine omega t plus D sine omega t. So that's my lucky guess. However, you have to go on to the next step, the modification rule. So you have to look like, do I need to modify this YP or not? So when do you modify the YP? When omega same as omega n, right? So that's basically the boundary there. So now let's separate, because I didn't specify my omega input frequency here. So now let's separate the situation. So let's say that case number one. Let's say when omega is not the same as omega n. So your input frequency. And by the way, what does omega n? What do we call omega n again? What do we call it again? Natural frequency. So that's great. So which means my input frequency is different from the natural frequency of the system, right? So let's see what happens. So if this is not the same, so then I don't need to modify this YP, right? So just YP is this, and all we need is just now to find the constant C and the D. Yeah. So there's actually nothing nothing tricky here. So you calculate YP, and then calculate YP double prime. Okay. So if I calculate this just slightly here, I'm not going to go into too much details. C omega negative sine omega t plus d omega cosine omega t negative c omega square cosine omega t plus d omega square, not plus, minus sine omega t, cosine, yes, sine. Yeah. Okay, so that's YP prime and YP double prime. Okay. Yeah. So now we sub this YP prime, YP double prime back into this undamped system and solve for C and D, right? Yeah. So then if we solve the C and D, we can solve the C and D like this basically. Okay, what we're gonna gain up with, okay, C equal F naught over M divided by omega n squared minus omega squared, and D equal to 0. Okay. Yeah, one of the assignments is for you to derive similar situations like this. Okay. Yeah. Okay, so this is a C and a D. So then my YP, basically there's only one term in here. So that means my YP is basically F naught over M omega n square minus omega square cosine omega t. Okay, so that's my YP. Yes.
How would you know if omega is the same or not as omega n?
Oh, yeah, well, here is a general situation, right? So we basically saying omega could be 3 or 4, whatever. So I'm using a symbol here. So, but I assume right now omega is not the same as omega n.
But you can use any one you want.
Yes, absolutely. Yeah. Where omega n is a known quantity. You give a physical system, omega n will be known, right? And omega is your user choice, so you can put in anything you want. So suppose now you're putting something that's different from the natural frequency. Then I'm looking at what will be the solution or response of the system. Yeah. Okay, so here's YP, and my general solution will be YP plus YH. Okay, so then general solution is Y equal to YH plus YP. So YH is A cos omega t plus B sine omega t, right? Yeah. So technically speaking, if you remember, I can combine two sinusoidal signals with the same frequency together, right? So I'll combine them together there. So the way to combine is the magnitude becomes square root A squared plus B squared. Then you have cosine omega nt minus certain amount of amplitude, a certain amount of a phase. Okay. Yeah. YP is still that term over there. Okay. So that's general solution here. Okay. Now the question here is, okay, here is a general solution with a certain physical system, and your input is omega. Now, so let's take a look at this responsivity here, right? See how does response change as we're changing our omega. Is that okay? Yeah. So let's take a look at this one here. Here's undamped system. Now you look at this responsivity. First of all, look at the responsivity here, right? So this is sinusoidal part. There's a constant amplitude A and B which depends on the initial condition. Okay? And the second term is another sinusoidal term. And the magnitude of this sinusoidal is this term. If you have your input parameter f0 and omega determined, then this amplitude here is also what? It's also constant, right? It's also constant here. So basically, what's changing here is this term is changing, that term is changing. So overall, you can imagine there are two sinusoidal signals and adding to each other, then technically speaking, you get another sinusoidal signal, right? Yeah, but it's not a regular one. Basically, it's something imposed, another one there. Okay. Yeah. So basically, now you look at this solution here. It actually makes much sense as we expected, because you're going to have a continuous oscillation. There's no damping, right? And it's not going to go away. So that's what happens here. Okay. Yeah. So number one, here there is a continuous, okay, vibration, okay, or oscillations, right? Yeah. And number two, now let's think about effect, right? Let's think about the effect of this input parameter. So what are the input parameter here? Input parameter, it's f0 omega. That's the input parameter here, right? Yeah. So let's say now, oh, I'm going to increase the input amplitude of the sinusoidal signal. So you increase this f0 here. So if you increase the f0, then you look at this one here. You're not going to be able to change this. This is part of the system here. So the only change is that here. So if f0 is changed, then this amplitude will change, right? If this amplitude changed, then overall you would expect the whole signal or whole vibration would have a larger amplitude. Does that make sense, right? Yeah. So that's changed. So f goes up, right? Then amplitude of this vibration goes up. Okay. So those are very intuitive thinkings here. Okay, so how about if I change this omega now? Basically change the input frequency, right? And how is that going to affect this output here? So if I change this omega here, it's not going to affect the first term. And it's going to affect this cosine. It's just going to be more frequent or slower, right? But now if you look at this term here, the amplitude is greatly affected by this omega value. Omega n, you can't change that, right? Omega n is the natural frequency. So omega is this value here. If you change this omega, it's going to affect this amplitude. How's that going to affect the amplitude? Basically, as omega is getting close to omega n, right? As omega is getting close to omega n, what happened to the numerator, the denominator? The denominator becoming 0, right? Yeah. So you're approaching infinite here, isn't it? Yeah. So basically, you would expect the output of this y becoming having a larger and a larger amplitude of vibration. That make sense? Yeah. So as omega, this one here, we're going to expect, okay, sort of an infinite amplitude. Okay, yeah. So that makes sense now. So basically, as omega, now at here, because now you've got to be careful here. This case here, this is the solution when omega is not the same as omega n. Okay, so this is not the solution when omega is the same. So all I want is to let omega approach this omega n. Okay, so I would expect an infinite amplitude at here. Okay, as t, basically as t goes to infinite. Okay, so now the natural question here is basically the second case now. How about when omega equal to omega n at here? Okay. Come again? Impulse response. No, it's gonna. We'll see that. So I think we mentioned all these things here. Basically, you don't want to stimulate the system with the same. Basically, you don't want to inject your system frequency with the same as, which is the same as the natural frequency. Okay, when that happens, the system tends to give this very radical and erratic type of a behavior. Yeah, Sean.
So it's not just omega is not equal to -1 in the first case?
Yeah, in this case, is when omega is not the same as omega n. No. Yeah. So when omega is not the same as omega n, you can see now this is still contained, right? It's still contained. Things are not crazy, right? Yeah. Even if omega is close to omega n, you can have a pretty large amplitude, but still it's contained. Okay. Yeah. So the expectation at here basically, if omega is the same as omega, so exactly the same thing, okay, exactly the same thing, then something bad should happen then here, right? So let's take a look at this general solution here. How is that going to validate our assumption? So all I'm saying is I'm going to expect something so-called resonant, okay, or resonancy. Okay, let's take a look at this. When omega is the same as omega n, and my yp at here, so the omega is same as omega n now, okay? Then I'm going to have to modify this yp by multiplying it t. Okay, so that's modification rule, right? So then yp will be c cos. So I'm not going to write omega anymore. I'm going to just write omega n now, right? Because now omega is the same as omega n. So then multiply everything by a t, right? So that's our lucky guess of the yp. Then we need to solve for for c and the d. That make sense? Yeah. Any questions so far? Yeah. So there's no specific numbers here, but I'm just sort of trying to study a general phenomena of a second order physical system. Okay. Yeah. So if I do this, I'll do the same integral, basically yp prime, yp double prime, and solve for c and d, right? And we'll see that in this particular case, our c is 0, our d is f naught over 2m omega n. It's actually not bad, right? Very simple c and a d. So that's the c and the d here. So which means the yp is basically just f naught over 2m omega n. Don't forget the t there. There's a t here. And sine omega n t. So that's yp, right? That's yp. Yeah. Then general solution is YH plus YP. So YH is still the same thing, right? Only changed one is YP. Okay. So the only focus here is, I guess, we need to focus on this YP at here, right? YP. So you take a look at this YP here. When omega is the same as omega n, how will be the change of the system here? Can we stop the chit chat a little bit here? Yeah. It's a little distracting from here. Okay. Yeah, remember the other day, the how's the salad thing? Actually, the student came to me because one of you guys was eating salad and I couldn't hear it, right? And was bumping on the bowls there, so he's actually not really talking to me. So anyway, this is a large classroom. Actually, for people standing in the back, I wouldn't be able to hear any noise there, so it's pretty quiet here. But in the front, I would. But some classroom in the on the campus like arts. Last term, I had my 254 over there, and that classroom is horrible because anybody talking in the classroom, I can literally hear it. You know, even if you think you're very low talking there. So it really depends, but I think you need to basically be considerate to your neighbors, huh? Yeah. Even if I can't say, even if I couldn't hear it. Okay, so let's go back to the YP at here. Yeah. It seems actually pretty obvious now. Why? Because you look at the YP here, YH is a constant oscillation here. So the YP here as t goes to infinite, and this term is constant oscillation. But this term, the amplitude, right? This term amplitude goes to infinite, right? Goes to infinite. Okay. Then overall the Y, right? So the amplitude of Y, which is the vibration, amplitude of vibration of the output, will also go to infinite, right? Yeah. So overall, I think what you expect, the output, right, would be more or less look like this. Okay. So initially, there might be some initial conditions, who knows, right? But let's say maybe no initial condition, but there's vibration, but then the vibration just keeps going up, 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 and then basically goes crazy, right? The envelope, okay, my drawing is not that good, but the envelope here, okay, the envelope right here, okay, is this guy, okay, it's this guy. All right. So that's actually this inherent so-called resonant condition. Okay, so you're putting a same frequency as your input, you induce the resonance of this system, okay, and that's no good. Yeah. So a lot of mechanical failure. Some of the bridges that probably you heard, you know, the Tacoma Bridge, they basically fail due to this mechanical vibration and due to the resonance of the condition here. So when you build something, if you check your CAD software or simulation software, one of the functionalities is to check this natural frequency of your object. So the reason is because you look at your natural frequency is how much hertz, maybe 1,000 hertz, maybe 10,000 hertz, right? Yeah. Then when you apply this system in actual situation, then you have to always bear in mind is there any possible external stimulus that will induce this frequency, right? So that's basically the reason there. So sometimes the wind frequency may not be as high as you think, but if your mechanical system just happen to have a low natural frequency, then something bad will happen, right? Yeah. So usually the natural frequency of a mechanical system generally will be very high. So then try to avoid some of the natural forces, frequencies of the forces. Okay. So this is the case when you have what we call this undamped system, right? Undamped system. So the second one here is a damped system. So damp system, the good part is you have a damping. Okay, when you have a damping in the system, okay, when you have a damping in the system, then you would never, okay, have this situation of this instability. So this situation here is what I call it unstable system. Okay, basically, as t goes to infinite, the system becomes unstable, right? Yeah. But when you have a damping, the B term in here now, you're guaranteed, as long as it's just slight B there, okay, as long as it's not 0. Okay, so then you're guaranteed that you will have a stable system. That's one thing, okay? So you will have a stable system. The general thing here, what I'm going to show you is most of the time people wouldn't like it, but let's try to shorten the writing at here. Okay, so here's the same system, except that we have this B y prime now. Okay. Now, same thing, I'm going to try to get the solution for the YH, right, for the YH. So unfortunately, the YH here is not as simple as the previous case. There's only one situation for the previous case. But for this particular case, the YH really depends on the value of MBK, right? So how many cases I have? I have 3 different type of solutions for the YH there. Do you remember that, right? Yeah. So in the free vibration, the lecture, I think I derived the YH, but I didn't use the MBK. I used a different set of parameter, which is zeta omega n. Remember that, right? So I'm gonna basically rewrite that, okay, using zeta and omega n. No. So you don't need to memorize all of these things here for sure. Okay. More of this understanding of what's going on. Okay, so you have 3 different cases basically, okay. And the zeta is the damping ratio. Okay. So this is the damping ratio there, and it's defined as B over 2 root Km, and omega n is the natural frequency, and this omega d at here, this term omega d is so-called damped natural frequency, because it's omega n square root zeta square minus 1. Okay. Sorry, it's actually 1 minus zeta squared. Okay, yeah. So that's YH, 3 different cases. So if you remember, what does each one of the cases corresponding to again? When zeta is greater than 1, what do we call that? We call that 2 roots, and basically it's over damped system, right? Yeah. When zeta is equal to 1, we call that critically damped system. And when zeta is less than 1, it's under damped system. Okay? Yeah. So now the question is YP. Okay? Yeah. So YP has to be based on the input function at here. So input is sinusoidal at here, right? So your lucky guess would be C cosine omega t plus d sine omega t. Now, for this particular case, you're guaranteed that you don't need to apply the modification rule. Why is that? Because when you have a damping at here, right? even if the solution is underdamped system, then you might have a complex roots. But you're going, because this damping there, this zeta, this term is not 1. So you will never, this term here will never duplicate the basis solution. Okay, so then you don't have to modify this one here, right? Yeah. So anyway, you do the same thing. You calculate the yp prime, yp double prime, and substitute in it, and then solve for C and D, right? So C and D. Okay, so this time the C and D are not as clean as previous case. Okay. So my yp, I'm gonna just basically shorten the writing it here. Okay, so we're gonna solve for C and D. And then we end up ourselves with a yp term, okay? Yp. So I have a C something here, I have a D something at here, right? Then ultimately, I will, because you see, this is a sinusoidal term. This sinusoidal, they're both omega here. So I can basically combine the two sinusoidal into one term, right? Yeah. So after combination, I'm gonna end up ourselves with yp just equal to E cosine omega t minus phi, right? And what's E there? The E, okay, is this. It's F naught over K. F naught over K. The K is a spring stiffness. Okay, and the root 1 minus R squared plus 2 zeta R squared. Okay. And the R at here is omega over omega n. Okay. So that's going to be your yp at here. Is that good? Yeah. And this phi, okay, this phi at here. Okay. This phi at here is, which is the phase at here, this phi takes also certain values. So we have the phi have two formulas. Okay. Number one is when omega over omega n is less than 1. Okay. So when the input frequency is less than the natural frequency, the phi term is this. Is tan inverse tan 2 zeta r over 1 minus r squared. Okay. And when omega over omega n is greater than 1, your phi is pi plus tan inverse. Okay. And here just 2 zeta omega n omega over omega n squared minus omega squared. So actually, same thing. I just kind of put that R into it now. Okay. So that's E and phi for the YP. Okay. Yeah. So bear with me with the writing here. All I want is actually just looking at, just explain what the YP is here a little bit. Okay. So, finish writing? Yeah, okay. And overall response is y plus yp, right? Okay, overall response. Okay, so now let's take a look at this overall response that is here, okay? So first for, as t goes to infinite, okay, as t goes to infinite, what do we have for the y here? Okay, what do we have the y? To look at the y, we have to look at the yh first. So this is yh at here, right? So what happened when t goes to infinite for the yh? 0. Yeah. See, you see this yh here. Every term, every yh, doesn't matter what case you have. There is this here, right? What's the zeta omega n is a physical system. They must be greater than 0. So this term here, they are exponential decay function. right? So as t goes to infinite, this term is gone. And so then all we're going to left with is this yp here, right? So this y will basically become yp. Okay, so for forced vibration with damping in the system, okay, then your y will eventually becomes yp. So this yh term in here, so this yh for this particular case, for this physical case system here, so we call it transient response. So why is it transient? Because it doesn't exist all the time. It will disappear, right? That's a transient response. Then this yp is what we call steady state response. So the name pretty much explains itself. Okay? Yeah. But understand that this is the case when zeta is not 0, all right? Yeah, if zeta is 0, that's the case for the undamped one, which is different from what we're talking about here. Okay? Yeah. Second of all, okay, the response of this system in here, okay, particularly if you look at this, basically, well, y will become yp, right? So then all we're going to do is we can just simply look at the yp here. That's basically what the system is going to show us. Okay. So if you look at this yp here, so the system will behave like this. The system will behave as a sinusoidal input with amplitude of e, and there's a phase phi here, right? And what's my input? My input is f cosine omega naught t, right? So remember what I said. When you have a linear system, when you inject the linear system with the sinusoidal system with certain frequency, certain amplitude, your output of the linear system will have the same frequency, but a different magnitude and phase, right? You see now? That's exactly what I'm saying here. So the E at here is not going to be different, not going to be the same as F naught, and phi may not be 0, right? Okay. However, you look at this E and the phi here. There's an expression with the E and the phi. So this is F naught over K. This R. What's R? R is omega over omega n. So the parameter omega n here is input frequency. So E basically is a function of the input frequency. Okay. So the E is the output magnitude. The output magnitude is a function of this input frequency. Does that make sense? Yeah. Look at the phase phi here. Phi, doesn't matter which case it here, phi is also what? Of the input frequency. So basically both of this amplitude E and the phase here, they are, so both the E and the phi, and they are function of omega, which is input frequency. Okay, so this basically is what I'm talking about at the beginning here, the frequency response. So this is basically amplitude, this is a phase. Then what you can do is you putting one frequency here, you get a reading of E and a phi. You're putting another frequency, you get an E and a phi. So you're putting as much as possible, you're putting a spectrum of frequency. You will have a whole bunch of data of the E, a whole bunch of data of the phi. Then you pull them out. The graph of this E and the phi is so-called frequency response of the system. Okay? Yeah. And that two graph, okay, will tell you lots of information of linear system. Okay, any questions? No.